Hello and welcome to Friday's edition of Cracking the Cryptic, and today we've got another colourful offering by the looks of it. This one is by Scott Strossal, and I'm sure if you've been following the channel for any length of time you'll be familiar with Scott's name. He's a wonderful constructor, and indeed he is behind the Sudoku challenge we're going to be releasing to you guys on Patreon on 14th of February, on Valentine's Day, so just around the corner now, Sunday. So yeah, do look out for that. That is a very stiff challenge, mind you. I don't know how hard this one is, I've not been warned, so but if it's anything like as difficult as that, then this video will be very lengthy. You guys will be able to tell, presumably, by looking at the length of this video, and you'll get some idea. Now, before I read you the rules, just to mention, Mark released on Patreon this morning his latest battle with the Times Club monthly special cryptic crossword. A very unusual crossword that, and every month it's probably the only crossword in that exists that stretches Mark at all. So if you want to see Mark beating his head against a brick wall, and who doesn't, then definitely check that out. What else to mention? Well, tomorrow is this remarkable sounding Killer Sudoku Marathon tournament over on Logic Masters Germany. Definitely have a look at that. It's going to be a race to see who can finish the 37 Kilo Sudokus in the fastest time. And if I get time tomorrow afternoon, I do plan to drop in on Clover's Twitch stream and just answer some questions. So if you have any questions for me, then hopefully I will be able to answer them tomorrow afternoon. All things, well, with a fair wind. I certainly intend to do it, but you know, life gets in the way. Anyway, anything else to mention? I don't think there is. I think we should just get on with the rules of Scott's puzzle. Let me read them to you. We have got normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage. So what that's telling us is normal Killer Sudoku rules apply. So those three cells there have to sum up to 15 without repeating a digit. So you can't, for example, put 2 4s in there, because although this cage does add to 15, and although it doesn't break the rules of Sudoku, it does break the rules of Killer Sudoku by repeating a digit in a cage. Don't do that, that's naughty. Now, this is the funny bit of the rule set coming up. Similarly coloured dominoes are clones of each other and must contain the same digits in the same orientation. So I guess what that means is that if that's a 6, you could just write a 6 in there. And then if that was an 8, that would be an 8. And if that was a 2, and that was a 3, yeah, what you couldn't do is that, because although these dominoes do contain the same digits, they don't contain the same digits in the same orientation. So if this was correct, that would also have to be correct. And that's all there is to it. So do have a go. Scott's puzzles are always great fun, and the way to play is to click the link under the video. Now I get to play. Let's get cracking. And actually, I should have been doing a palindrome puzzle today, shouldn't I? That is remiss of us, because today is the 12th of the... Well, the way we write it in Britain is 1202-2021, which is a perfect palindrome. And in fact, someone wrote to me earlier to say not only is it a perfect palindrome, but it's also sort of an ambigram, because if you type it into a calculator, 12022021, and turn the calculator upside down, it still reads the same, which is lovely. But nothing to do with solving this puzzle. Sorry, I digress. Let us get back to this. How do we solve this? We can... well, I can let you in on a little piece of magic in box 1. Look, what do those squares add up to? Well, a complete box of the Sudoku will contain all the digits 1 to 9, and therefore it will add up to 45, because that's what those digits add up to. Now, if that cage is 17 and that cage is 12, that's 29. So those squares have got to add up to 16, which means they are 7 and 9 in some order. Now, we've nearly got the same there. It's not quite as good. These ones have got to add up to 15. In fact, look, we've got 12 cages. Symmetrically arranged. Now, I am not going to be misled by this puzzle, because last time this happened and I spotted this pattern in the grid, I spent about 15 minutes of the video talking about Fistomefel's ring and how I think there is a variant of Fistomefel's ring which says that these cells here are the same as, I can't actually remember what they're the same as. I think they're the same as, that's only 12 cells, maybe in the corners. I'm not exactly sure, I can't remember. Anyway, and I spent about 15 minutes of the video proving that, and it proved to be a total red herring, so I'm not doing that again. Anyway, let's carry on with maths. Maths might be our friend. We've got 15 there as well. This one is another, yeah, this one is the same as that one. 17 here, 12 here, that's 29, so those must be 16, they must be 7 and 9. So, don't think we can use this pattern to disambiguate which version of the 15s we've got into those squares, but I might be wrong. What we can do, a 12 cage in 4 cells, there's 2 things I know about that. The first is that there are only 2 ways of making 12 in 2 cells. 12 in 4 cells. 1, 2, 3 and 6, 1, 2, 4 and 5. Now you will note that the common digits there is always 1 and 2. You always have to include 1 and 2 in a 4 cell 12 cage. So that might be interesting because of the... So that means that this cage always has a 1 and a 2 in it, because we know if we look at row 1 now, those cells can't be 1s and 2s, those cells can't be 1s and 2s, so the 1s and 2s are forced into the 16 cage, and that's going to go round the grid. Look, it's the same effect everywhere. So that's certainly a little bit interesting. 3, if that was 1, 2, 3, 6. Yeah, I've got something here. I've got something here. So let's imagine this one was 1, 2, 3, 6 for a moment. Here is a question. What would the makeup of those two 12 cages be? Well, the answer is not 1, 2, 3, 6. Because if you try and put 1, 2, 3 and 6 into either of these 2x2s, you've broken the puzzle. Because now, ask the question, where do 1, 2, 3 and 6 go in row 1 of the grid, or column 1 of the grid? The answer is they have to go, they don't go there, they don't go there, so they have to go into those 3 cells. Well, here is a knowledge bomb from Cracking the Cryptic. You cannot put 4 different digits in 3 cells of the Sudoku without giving yourself a very serious problem. So they form like a checkerboard then. So if this is 1, 2, 3, 6, this will be 1, 2, 3, 6. And if this is 1, 2, 4, 5, well, if this is 1, 2, 4, 5, these will both be 1, 2, 3 and 6. Now, what does that mean then? Does that mean anything good? It means that, so if this is 1, 2, 4, 5, I get 1, 2, 3, 6 here, 1, 2, 3, 6 here, 1, 2, 4, 5 here. I'm sure this means something profound, but I'm not exactly sure what it is, I'm afraid. Oh, bobbins. 1s and 2s in here. I don't think that impacts the 9 cage. I've not used the clones at all. I've got a horrible feeling, you know, I might have to use Fistomefel to crack this. Let me just try. if you don't mind, I'm just going to spend no time at all. Well, not literally no time at all. I just want to think about whether or not this is going to be helpful. Because I think it's the corners. If it does look like it's helpful, I will check what this is. I'll try and prove it. So the reason this is interesting is that if this is right, I would know exactly what was the digits in the yellow squares in the perimeter. They would have to include... Oh, this is definitely important, I think. This is definitely important, because if I've got to put 2 3s, 2 4s, 2 5s, 2 6s into the perimeter... Oh, yeah, yeah, okay, look, you can't put 3s in here. This is very... Right, this is beautiful, but tricky. Now, I'm just wondering if I'm even going to be able to show the Fistemafel ring, given I've already got colours in this grid. I may have to... I'm going to pause the video. This is very rare, and what I want to do is just give myself a blank Sudoku grid, because I think to show you this, I'm going to and to show myself it actually, and to prove it to myself, I'm going to have to do that. So 1 second. Okay, here we go. I've got a blank Sudoku grid. So what we're going to do is we're going to try and show what the relationship is between these cells and some perimeter cells in the grid. Now, what I might do is I might do this with set equivalent theory, because we've done a lot of videos before where we've proved the remarkable thing about this shape. This is the classic Fistemafel ring, and if you've never seen it before, be prepared to have your jaw dropped, because basically the green cells are exactly the same digits as appear in the Fistemafel ring. So these 16 cells are exactly equal to these cells, and we can show that. I've done lots of videos where I've shown how to do that, but I don't think I've ever done it using set equivalent theory. What is set equivalent theory, you might be asking? Well, it allows you to say things like this. This is the set of digits 1 to 9. That's the set of digits 1 to 9. And these two things contain the same set of digits. Now, I appreciate that that might not seem very profound to you, but that is basically what set equivalent theory is. It's shading the same size region. It doesn't have to be the same size regions, but it's shading different bits of the grid and then forming a relationship between those things. So we can, to make it a bit less trivial, if we were to say the purple squares equal the set of the digits 1 to 9, let's think about that in the context of row 5 of the grid. Now, if we were to remove from that set of the digits 1 to 9 these 3 squares, these 3 digits, whatever they happen to be, if we just take those out, could we say anything about these cells? Well, we could say that these cells, these green cells here, must be the identical digits to the purple cells. And this is a another very simple example of set equivalent theory. How do we know this? Well, we know that the purple regions, the purple cells now, these 6 purple cells, are equal to one set of the digits 1 to 9, because that's what we'll find in this box, minus the white cells. But we also know that the green cells are equal to one set of the digits 1 to 9, minus white cells as well. So these sets are the same, and you can see that very easily via Sudoku as well. Now, let us therefore think about how can we think about these? So let's make those purple. So that suggests to me, at least, we must start, in terms of this whole set equivalence theory, we must start with 4 corner boxes. So let's start with 4 corner boxes. Yeah, okay, and we're going to have to deduct these. Right, okay. So I think this is how we're going to do this. Do we agree? Let's start with this. Do we agree that the purple squares are 4 sets of the digits 1 to 9? Hopefully we all agree that is true. So if what I think is easiest, let's split those 4 sets of the digits 1 to 9 that appear in the purples, and I want to consider each of those sets once each. Okay, so let's take the first set of the digits 1 to 9. I just want to think about one of the sets, and I want to think about it in the context of column 1. So this, obviously, what I've just highlighted is also one set of the digits 1 to 9. Now, if I remove from the purple cells these squares and these squares, I think we'd all agree that I've removed these 6 cells from one of the 4 sets, complete sets of the digits 1 to 9. Yeah, those are all different digits, quite clearly. They're all in the same column, so they must all be different. And I can remove these different digits from just one of the sets, so I want to remove them. Now, obviously, these green cells here, these green cells are left inside the purple cells somewhere, because in relation to that one set of the digits 1 to 9 that I was focusing on in the purples, if I remove those 6 cells from that complete set of the digits 1 to 9, I'll be left with the green cells, because obviously this column works in exactly the same way. So this is the key thing to realise, is that the green cells now, whatever is in these green cells, must appear somewhere in these purple cells along with 3 complete sets of the digits 1 to 9. And this is the whole basis for set equivalent theory. And we can check that. That would imply that there should be 30 purple cells left, because there should be 27 cells, which are the equivalent of 3 sets of the digits 1 to 9, plus my green cells. And if that's 9, that's 18, that's 6, that's 24, and that's another 6, so that's 30. So let's do this again. Let's look at column 9 of the grid. And this time I want to focus on one of the complete sets, one of the 3 complete sets of the digits 1 to 9 that I haven't yet adjusted in the purple cells. So at the moment, when I did this on column 1, I just played with one of the sets. So I've got 3 complete sets left in the purples. Now in relation to one of those complete sets, I want to remove those 6 digits from that complete set. Now if I do that, if I remove those 6 digits from the purples, you can see that those 3 cells, whatever is in those 3 cells, will be the remaining digits in that set in the remaining purples. So now my purples consist of these 3 cells, and 2 complete sets of the digits 1 to 9. Now let's do the same thing in row 1. And I want to think about row 1 in the context of one of the 2 remaining complete sets of the digits 1 to 9. So if we think about row 1 and I look at one of those 2 remaining complete sets of the digits 1 to 9 and I remove from that set those cells, take them out, then in relation to that set I'll just be left with whatever those digits are, because this whole row is the equivalent of one set of the digits 1 to 9. So if I remove those cells from the purple, I'm removing these cells from one set of the complete digits 1 to 9 within the purples, I will be left with these cells here in the purples as the remainder of that complete set. And then we obviously can do the final thing at the bottom. We've only got one complete set in the purples that we haven't adjusted yet. I'm going to remove those 4 squares from that. I will be left with these 5 squares, and we should find, if I haven't made a mistake, that I have got 16 purples, which I do. I should have 16 greens, which I do, and these digits are the same. And that is really lovely. So that's just a different way of proving it. Normally I wouldn't prove it that way, but I wanted to do it in a slightly set equivalent theory way, because it's really popular over on the Discord server at the moment. There's quite a lot of chat about Sudoku theory over there. So if you're interested in this sort of stuff, and if that made no sense to you, go over there. They'll be able to explain it much better than I can. Now, let's go back to the puzzle then. And see, does this matter? I've now got to get my head around what was going on in the puzzle. Yeah, no, I was thinking about threes. Yes, because now I have proved that the 12, whatever goes in these 12 cages, goes in these cells round the perimeter. Now, because we've worked out that the 12 cages are made up in a very particular order, we know there are going to be 2 12 cages that contain 1, 2, 3 and 6, and there are going to be 2 12 cages that contain 1, 2, 4 and 5. Now that means that these cells round the edge, which must be those exact same digits, have to include 3s in them. Where do we put the 3s? And this is what I noticed before. Because I've got 1s and 2s in these 16 cages and 17 cages now, I can't put 3s in them. It's impossible. So where do I put the 3s? Well, that means the 3s have to go in the corners, and the 3s have to go diagonally opposite each other, because if I put a 3 here, I can't put a 3 in either of those without breaking Sudoku. So I think what this is telling us is that the 3s are either aligned that way or they're aligned. In fact, that one is in a clone. Oh, that's right. This is gorgeous. Right, so this can't be the pair of 3s. Because if this is the pair of 3s, this grey clone says put a 3 there, which is a 21 cage in 3 cells. That does not work for us. So that's not 3. So if these aren't the 3s, the only place you can put the 2 3s in this puzzle, in these squares around the perimeter, which we have proved must contain exactly 2 3s, is those 2 squares, QED. That is absolutely beautiful. And probably useless looking at this. What? No, come on. What does that mean? What does it mean? It means... I can't actually see what it means though. No. I suppose it means we know what the... Yeah, okay, we know which way round the 12 cages work now, don't we? So this 12 cage can't contain a 3. So that must be 1, 2, 4 and 5. The same thing is true of this one. Now that means this one and this one must be 1, 2, 3 and 6. That means the red... okay, so maybe we use the clones now. I've got 1, 2, 3, 6 in the red clone, so that means, yeah, look. So these squares are 1, 2, 3 and 6, but the 3 here sees those. So this is 1, 2 or 6. And this blue clone is 1, 2, 4, 5. And that goes down there. And that means, look, so that can't be a 4, 5 pair now, because then you'd have to put 0 into this square. So what does that mean? If this can't be a 4, 5 pair, I'm not sure. But look, actually, now we know this is 1, 2, 3 and 6. We know the exact order of... We don't know the order, but we know what's in that 17 cage now. So that's 4, 5 and 8. And that includes a grey clone. So those squares are now 4, 5 and 8. Now, they can't be, that cannot be a 5, 8 pair. Because if it's a 5-8 pair, that will add to 13, and I need another 8, and you can't repeat 8 in the box. So there's definitely a 4 in there, which means there's definitely a 4 in here, which, that means that's not a 4. That's not a 4. That means that one is not a 4. This feels like very much worrying away at... Now hang on, I've got digits here as well in a clone. 1, 2, 4, 5 over there. Sorry about this. I'm sure that I'm meant to know what to do here, but I don't. So I now know this one. I know what's in here. Look, that's got to be a 6-8 pair by Sudoku. Do I know what's in this pair? So I can see if I knew there was a 6 in this pair, it would disambiguate this pair. So, right, okay, so if I know that there's a 1 or a 2 here, that would cause the 6 to be in there. So let's just think about that. I know this isn't 4, 5. Yeah. Okay, now look at the blue clone. Because I've ruled out 4, 5 from this domino because that would cause this to be a 0. But how about, is it possible this is a 1, 2 pair? Well, no, it's not. Because if this was a 1, 2 pair, this would have no value because we know that the 1 and the 2 in this box here are definitely actually in the 16 cage. This can't be a 1 or a 2. So this is a 4 or a 5, which means that's a 4 or a 5. But that means this can't be a 5 because we know that this is not a 4, 5 pair. So this is not 4 or 5. This is not 5. And now what is this domino? What has this domino got? What's it got in it? Well, it's got one of the digits 4 or 5 and one of the digits 1 or 2. And that means there is a virtual 1, 2 pair in this row between one of those two squares and one of those two squares, which means this is not a 1, 2 pair. Because if it was a 1, 2 pair, you couldn't put 1 and 2 in that 12 cage. So one of these two squares is our old friend the 6, and that matters because that 6 goes down here and that 6 sees that square, which now is an 8, and that's a 6. This is very cool. Now this 8 here means that's a 5, look. That's going to fix this domino. Just let me just check I'm not missing things here. So now this is a 4, 8 pair, which means we need a 9 to make this add up to 21. Now, does that matter? The answer is quite possibly, but I don't know how yet. Now, 1 second, I've got to think about this. So I've got greys. The grey is definitely 4 or 8. I've got 6 down here. Oh, I'll tell you one thing. Once you get a 6 down here, that means these 3 squares are a 1, 2, 6 triple, doesn't it? Because we know there's a 1 and a 2 in this triple. So these add up to 9, which means that is 8. 8, 8. That is 8 by Sudoku. Look at this box now. 8 is in one of those 2 squares by Sudoku, so it's not here. So that's a 4, that's an 8. That goes through the clone. 8 by Sudoku now is locked into exactly one place in box 2. I think it's in one of 2 places in box 4, and I'm not sure I know that even that much about. I think it's one of 3 places in box 6. these two squares have got to add up to 7. One, 2, 6. Oh, hang on. Yeah, now we can go right back to the logic we did at the very start of the puzzle when those squares added up to 30 and we knew these two had to add up to 15. We've got 8 in one of them now, so that becomes a 7, which fixes the 7 and the 9, which fixes the 9 and the 7. Does that fix everything here then? Oh, I think it does. There may be a simpler way of looking at this, but we know those two squares add up to 15, so they must be 6, 7, 8, and 9. And look, this has got 6, 8, and 9 looking at it, so that's a 7. This should be an 8. And these squares now are 4, 5, and 9, which do add up to the right number. And there's a 9 there, so we get the digit. We get the 9, we get a 4, 5 pair. That's causing a 4, 5 pair in this column, so that's not 4 and 5. This must be a 4 or a 5. The 4 here sees it, so that's 5. That's 4. That goes through the clone now, so this is 4. The clone is in a 9 cage, so you can't put 1 with it, because then that would also be a 4. So this is 2, I think, and that's 3. Which means the clone, that's 2 and that's 1. Now we take 1 out of these two squares. This clone becomes a 2, 6 pair. The 2, 6 pair means this is a 1. Good Lord. I mean, it's just a stunning puzzle, this, isn't it? 1, 3, and 6. So this square is a 3 or a 6 because it can't be a 1. We know the 1's over here. In fact, I'm sure, look, 4 up here. I was just thinking, we must know what this is now, don't we? These two squares are adding to 15. They're 6 and 9. 9 here tells us the order. Sorry, yeah, that's been sitting there for a while. These squares now are 1, 2, and 5, which add up to 8, which means this is an 8, which means this is an 8. Oh, look, sorry, 31 cage, the cross adds up to 31. Add 10 to that, that's 41. So these two squares have to add up to 4 to make 45, which means they are a 1, 3 pair. 1 can only go there in the top box now. It's been ruled out of those two squares. 2 is now forced into this square. Oh, in fact, now that's going to give us that one. That's a 6. Those 3 add up to 9, which means we need a 7 here. This 2 fixes the 2, 6 at the bottom. These 3 squares, oh, they're 1, 2, 5 as well as those squares. Okay, well, that seems to be what it's telling us. Those add up to 8, so this must be 9. 9 goes here by Sudoku. So 9, look, where does 9 go? In this box. By Sudoku it goes here, which fixes the 20 cage with a 3 and a 1. These squares are not 1 anymore. The 15 cage gets fixed. We needed 7 more, so this becomes a 6. That 6 is huge because it fixes the 6 and the 2, which I could have done another way. It was ever thus, I'm sorry. There's no 2s there. 1, 2, 5, so we need 3, 4, and 7 into those squares. And there's a 3, 4 there, so that's a 7. This is a 3, 4 pair. This is not 2. This is not 2, so I've now got a 1, 5 pair in row 6. And I need to put a 6 in it, which will have to go here. That's a 2, 3 pair. There's all sorts going on. I am aware that I'm missing things right, left and centre. That's what it feels like anyway. This is a 2, 4. So this becomes a 1, 5. The 1, 5 has a clone. So that's a 1, 5 pair, which fixes a 2 here. Fixes a 5 over here. That gives us a 1 and a 2. This 1 disambiguates the clone. This is just stunning. 1, 6. What I love about it is it's a lot of fun solving this. and it's not monstrously difficult, and that's no bad thing. 4, 7, yeah, we can do that. That's a 4 by Sudoku, I think. That suggests we need a 7 here, which does seem to complete the box. 5, 6 and 7 into those squares. That's a 5, that's a 7, that's a 6. And we're just left with this box where we need 3, 5. Oh, I still haven't done the 9s. Gosh, I'm so silly. 5 and 3. And that seems to be all the digits. The clones look like they're working. We click tick. Yes. Loved it. Absolutely loved it. Thanks so much to Scott for that one. And I hope you guys enjoyed my talk through of it. Yeah, and if you have questions about the set equivalent theory, do drop a comment and let us know. But yeah, I did that slightly differently, and I will try and remember to put a link in the video to sort of the more classical explanation of the Fist-Fell ring. But what a puzzle. Really, really cool. And we'll be back later with another one from Cracking the Cryptic.